Hey everyone, it's Mr. Tate. I wanted to go through some of these problems that are on your review. You guys know that you have to do the whole review, turn that in with your guided note packet. You guys should be able to access the review, well, at least the review and the version where I have the selected solutions. I'm going to be going through and explaining some of those problems a little bit more in detail, okay? Starting with 1A, determine whether the relation is a function and then explain. Now remember, for a function, every input can only have one output. And you can reference our old videos. You can have an input go to an output more than once as long as it's the same output. But as soon as it goes to a different output, then it is no longer a function. So looking at 1A, I'm looking at my inputs right now, and I notice that -1 does not repeat in either of these, or any of those. 0 doesn't repeat in any of these. 1 doesn't repeat, 2 doesn't repeat, and 3 doesn't repeat. So I don't actually have to worry about failing this condition of being a function. And it is indeed a function then. Okay, and your reasoning can be something along the lines of because every input has exactly one output. Okay, so I'll leave 1B, C, and D for you. Let's check out 2A. Same deal, just recall that my inputs are my x variables. So in an ordered pair, they are the first number that shows up. So I'm checking to see if any of my inputs or my input values repeat. Starting with -10, it doesn't repeat here, here, or here, but it repeats there. So already it's not going to be a function. You guys will notice also that -8 repeats twice right there. Okay, so it's not a function. The inputs -10 and -8 each have two different outputs. And then you might write specifically what they are. If you look on the key that I put the specific outputs that they go to. So each have two different outputs. Cool. So that's the first checking to see if a table or a set of ordered pairs represents a function. Let's go ahead and get into 3, 4, and 5. Find the domain and the range of the function represented by the graph. Now, remember, domain measures or actually indicates all the x values that show up on your graph. And your range are all the y values. So if I'm looking at 3, and 3 is kind of a nice introduction because they are specific ordered pairs. And let me highlight them for us. There's one right here, 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 and there. And what I want to know for my domain are those specific x values at those points. So it's kind of, if it helps, you could write them down as ordered pairs, where this one would be 0, -5. That one would be 1, -3. Right there would be 2, -1. Right here I have 3, 1, and right here I have 4, -3. And I'm going to go ahead and all of my x values, because that makes up my domain, let me highlight them in the same color. Okay, and I will list them all out. So I'm going to write them in increasing order, and the smallest one is 0. Next, I have 1, 2, 3, and 4. That's my domain. Now let's check out our range. Let me highlight these in purple. I've got -5, -3, -1, 1, and I actually have -3 show up twice. So I don't have to write that one twice. If you do, it won't mark you down, but I've got -3, -1, and 1. Okay. You might, if you missed out on the last couple seconds where I said you don't have to write down the -3 twice, you might notice that you've got 5 values for your domain and only 4 for your range. It may work out like that or vice versa in different problems. Here it's just because the -3 shows up twice and I don't have to write it down 2 times. Let's move on to 4. Now, or 4a at least. Same deal, I'm looking for my domain and I'm looking for my range. Here I don't have ordered pairs, and I actually have just this continuous graph that has no little specific points. Okay, now if I'm measuring my x values, the key thing to notice is I have these arrows here, which means that this graph, even though I am only seeing it in this window here, it continues on, and I'm going to erase this in just a moment, but I would expect this graph to keep going down here if I made the little graph a little bit bigger. Okay, so even though I only see a certain part of it, it doesn't mean that it's stopping. Now, for my domain, I notice that in this left direction, it is going down, but it is also going to the left. And as far as going to the right, it is going down, but also to the right. And it's going to go down to the left forever and down to the right forever. So both directions will actually be covered. Now, sometimes you hear it referred to as negative infinity and positive infinity. And because our domain covers all of those numbers, another way to say that is just saying it covers all real numbers. Now, when I'm looking at my range, I can't actually say all real numbers because, let me erase this for a second. There is a point where it stops. Now notice that it never gets higher than this point. So I have to use an inequality to represent my range. Now, at this value, it would be 3. And y never gets higher than that, it only goes lower. So y is always lower than 3. Because there's not a specific open point there, I can use the less than or equal to sign. Okay, and that would be our range. Check out 5a. 5a is a little closer to 4a, but notice that it doesn't have the arrows. So what I see is all that it would cover. Now I can't say all real numbers then for either because they stop. They don't go left and right forever, or they don't go up and down forever. So if I'm looking at my range, I'm looking at from left to right, and let me make these kind of barriers or like boundaries. So if I'm considering my domain for now, I'm considering my x's, and that's left to right. And this window here is all that I'm considering for my domain. So let me get to here. It looks like the smallest value is at -3. The biggest value is at +3. And anything in between works. And since these are closed circles, I will put less than or equal to signs, or put that or equal to sign for both of them. Okay, so let me erase this and let's consider our range. And I will do that in purple. And then kind of similar to how I made the boundaries left and right, this time it's going to be the bottom boundary, and the tallest boundary is actually up at the top there. Okay, so let's see. Notice there's no like break in there, so I don't have to worry about getting like breaking it up into chunks. The lowest point here is at -1, and the highest point is at 3, and our range is representing or measuring the boundaries of our y. And because they're the closed circles, they have the or equal to sign underneath. Okay, so that is 3, 4, and 5. Let's go through 6, 7, and 8, at least one of them for all, and then we'll kind of stop this video and then pick up on number 9 on the next one. Number 6, 7, and 8, we're trying to determine whether the graph, the table, or equation represents a linear or a nonlinear function, and then we'd explain. So 6 is fairly easy to look at least for 6a. I notice that I have a straight line, and then notice that in linear we have that word line. So I'm going to put yes, well, I don't necessarily put yes, but at least put linear, and something along the lines that the graph is a line. Now you might be able to look at 6b, 6c, and 6d and notice that some of them may and some of them may not be straight lines. If they are not a straight line, then it's not a linear function. Let's check out 7. Now 7's a little bit more work involved. I've got to look at my x change and my y change. Now if my x changes at a constant rate but my y's do not, then I do not have a linear function. If they do, then I do have a linear function. So I'm going to check real quick. From -5 to 0, we are going up 5. From 0 to 5, we are going up 5. So that part satisfies so far. From 3 to 7, we are going up 4. But 7 to 10, we are going up 3. And what I really wanted for this to be linear is to say +4, and it does not. Okay, so that right there makes this a non-linear function. Okay, as x increases by 5, y does not increase at a constant change or rate. And then lastly, let's check out 8a. For here, I've got to simplify a bit. I've got x times the quantity of 2 minus x. Now remember, this is an example of using the distribution property, or the distributive property. And I'm going to multiply the x times the 2 and the x times the negative x. So since this is a positive x, I will put a plus x right here. And simplify. I have 2x minus x squared. Now, because I have this exponent of 2, I know that this is going to be nonlinear. Because there is an exponent of 2. And recall that for a linear function, the only powers that I can have are all degree 1. So it's either degree 0 technically for a constant, or they're 1. So like for the y, if I had to put an exponent here, it would be 1. For the 2x, if I had to put an exponent on the x, it would be 1. But this part fails. And you can also notice on the review, you cannot write this in the form of y equals mx plus b, which is slope-intercept form, which is something we'll get into next unit. Okay, that's 1 through 8. We'll pick up on 9 in the next video. Okay, picking up on 9a, evaluate the function. Okay, so let's check this out. Remember, we read this as f of x. Okay, this is not f times x. And over here, when they have this f with a number in it rather than a variable, they want you to plug this number in for any x. Okay, so I'm going to go ahead and rewrite f of -4 is equal to, let me change up the color here so I can see the negative sign clearly. I will put a parentheses where there was an x, and then in a moment I will fill it in with this -4. Okay, and right here I'm just going to be solving. I know that I've got a negative and a negative, so that turns this into a +4. Okay, really what I'm doing is saying -1 times -4, and that is equal to +4. And then I still have the +4, and I get 8. So f of -4 equals 8. For 10, we've been looking at a table. So the table actually should be, these should be one of the easiest problems on the test. If I'm looking at f of 2, remember that this is replacing the x variable. So I'm looking at the x, looking for where I find 2. That's a little, maybe a little. And I get it right there. Okay, at this input, my output will be 13. So let me go ahead and write that down. 13. F of 7, I'm looking at where x is equal to 7, and the output would then be 22. So I've got f of 7 is equal to 22. Checking out 11, I've actually got a few values to find, starting with f of 0. Recall that this is replacing the x, so I'm looking on my x-axis where it's equal to 0, and it is right there. Gonna find where does it hit my graph and what is the y value at that point. So it hits the graph right here when x is equal to 0, and that value is -1. If I look at f of -3, f of -3 would be right there because my x is equal to -3, and I'm going to go down to this point right there, and notice that this value here is -3. And lastly, I have f of +3. I have my +3 here, hits right there. The value of y at that point is 1. So f of 3 is equal to 1. All right, checking out 12, and I'll probably do a couple here because just a review for discrete or continuous. Determine whether the domain, that's my x values, recall, is discrete or continuous. Now, I don't have a graph here, but remember, if I wanted to consider something that was discrete or continuous visually on a graph, that would be whether I can draw the graph without picking up my pencil, or do I have to skip around, wherever it might be, okay? So in this case, let's apply it to this example where our inputs are hats, and the output is the cost. Now, this is an example of a discrete domain. The reason being is that the number of hats must be measured in a whole number. So yes, I'm sure you could go somewhere and buy half of a hat, but typically we don't think about buying hats in terms of fractions or parts. It's either you bought a hat, you bought 2 hats, you bought 3 whole hats, or more. Okay, so, and it's pretty evident here where it's 2, 3, 4, and I guess maybe that's not the best example because when we get to 12b, it seems that way too, but just think about, can I buy that or could I have 2.1 hats? And typically no. So this is a discrete domain. And then your reasoning can be something like the number of hats must be a whole number. Or whole, like you just, or something along, you can't buy part of a hat. Okay, now to show you kind of the opposite, if I was looking at 12b, where I have the depth, and when I'm thinking depth, I'm thinking maybe something like a submarine or a scuba diver, something as far as how deep something goes. And usually I think of water for some reason. I'm sure there's something else you could relate it to. But this is an example of continuous. Because although they do give me whole numbers here, the depth could be any number of feet. So for example, like if I was measuring your height, you could be 5'7" and an inch, and a quarter inch. So you didn't necessarily have to be 5 feet tall or 6 feet tall or 7 feet tall. We can have stuff that's in between. We can have your height measured in decimals if we really wanted to, where you have actual numbers besides 0 after the decimal. So this is continuous. The depth can be any number. Thinking about like if you were a person and you were going to be diving, I don't know, that's not my strong suit. But for example, if you were a person swimming in the water and then you decided to go down, maybe you've got some scuba gear. I don't know. And say hypothetically you went down to 33, 66, or 99 feet. You would imagine that at like some point your head would be maybe half a foot below. And the fact that you are using a fraction, not a whole number foot, is proof or part of the proof to show that it would be continuous. Like you're not just transporting to 1 foot, 2 feet, 3 feet, and never be anything in between. Okay. I don't know if that makes it more confusing, but just consider that, especially any measurement of distance, you can have anything in between. Let's go on to 13. I guess it should be find the value of x that makes each output or each given output true. So this should be find first. Find the output of x that makes each given output true. A little bit different than when we were evaluating the function. Here we are saying, well, what would this x have to be to give me -3? Okay, so that's what we're looking for. So if we want to know what x that would have to be, we have to solve for this x. And if we know that we want this to equal -3, then let's replace w of x with -3 and rewrite everything else. And then this becomes a simple solve for x equation problem, where here I'm going to subtract 7 from both sides. -3 minus 7 is -10. And then I have the -2x that follows. Divide both sides by -2. That reduces to 1x. is equal to 5. Now, if you wanted to double check, what you could do on the side is say, well, let's check w of 5. That would be negative 2 times 5 plus 7. Negative 2 times 5 is negative 10 plus 7 equals negative 3, which matches with what we wanted. Let's check out 14. For each of the following, use the given function to solve. Okay, for 14a, we've got the function d of x is equal to 1375, or 1375, minus 110x represents the distance in miles a high-speed train is from its destination. Part A, how far is the train from its destination after 8 hours? So to break down what this formula does, by plugging in a different value for this x, that tells us how long we've been traveling for. So if I plugged in a 5, that would be representing 5 hours. If I plugged in a 2, that would be 2 hours. And this whole function tells me how far away I am from wherever I'm going. Okay, so if I want to know how far away from the destination after 8 hours, then all I'm going to do is plug in 8 to my function. 1375 minus 110 times 8. Okay, and then I've got to do 1375 minus 880 and simplify this a bit more to get 495. So to respond to this question, we would say you would be 495 miles, or 495 miles away. Part B, how long does the train travel before reaching its destination? Now, here it is very similar to problem 13, where we want to find the value of x, or find the value or the number of hours where we are no longer any miles away from our destination. So that would literally mean what we want to know is, when is d of x equal to 0? Okay, so let's use this, rewrite this function real quick. 1375 minus 110x. When is this going to be true? And I will say I want to know when it's 0 miles away, because that means you are actually there. And then this becomes just like 13a, solving for x. Here I'm going to add 110x to both sides and get 1375 is equal to 110x. Divide both sides by 110 and get x is equal to 12.5. So in terms of my question, this means it takes 12.5 hours to reach your destination. Okay, I'm not sure where we're at in time, so I'm going to stop here and we will pick up at 15 on the next part. All right, 15, we're finding the inverse of each relation, and 15 and 16 actually. Now remember, when we're finding the inverse, our x's and our y's are switching. So this problem should be rather simple. When I write my ordered pair down below, the x value becomes the y value, and the y value becomes the x value. So I'm going to do the same for all of the others. And think about what the last one will be. 8, 6. Same thing for if you have a table. So I'm flipping my inputs with my outputs. My input becomes the output if I took the inverse. So I know I kind of blocked this out, but this says -3. my output is then -3, and then the new input would be 4. So all of these I'm switching. 2 is my new, 2 is my new input, and -1 would be the new output. So I'm going to go through and switch these. And then 3 and 3, they switch, they're the same number, so it looks the same. Let's check out 17. So find the inverse of the function. So remember our steps. First thing we do, we replace f of x with y. Second thing we do is switch any x with y's. So any y gets replaced with an x and vice versa. So switch the x's and y's. Third step, we now solve for y. And lastly, once you have y all solved, let's see, green, replace y with f inverse of x. Okay, so the key part here, it looks like a normal f of x, but it looks almost like an exponent with the -1. So let's do that with 17. And then we'll do 18 afterwards. So first thing I will do, replace the f of x with y. Okay? Second thing that I'm going to do is switch out my x's and my y's. So I'm going to put an x there and a y there. Third thing I'm doing is solving for y. So in this case, I need to subtract 3 from both sides. And I get y is equal to x minus 3. Now that I have y all by itself, my very last step is to rewrite this so it says f inverse and put f inverse of x is equal to x minus 3. So I did a couple things here. I switched the y, but then I kind of flipped the equation. So now the y is kind of on the left and the x minus 3 is on the right, and that's totally okay. Let's do it with 18, which I know if you're looking at it, it looks slightly tougher just because of that fraction. I'm going to do the same steps though. First thing, replace the h of x this time with the y. Second, I'm going to be switching my x's and switching my y's. Third, I'm solving for y. So this one might take an extra step or two, but we can do that. Subtract 6 from both sides. Cancels out right there, and I have 2/3 y is equal to x minus 6. Some of you guys might feel comfortable multiplying both sides here by 3/2. I'm going to chunk it up and get rid of the denominator first by multiplying it by 3. And I'll multiply this side by 3 as well. The reason being is this 3 and this 3 will cancel each other out, and I'll get just a 2y on the right. And then I've got 3x minus 18. Okay, now let's pick up this work right there, and I'll just rewrite that, and I'll rewrite it in pink again. And let me go ahead and put the y's on the left side. So this is fine. Secondly, I'm going to, or maybe not secondly, but divide each by 2. And I get y is equal to 3/2x minus 9. The very last step, switch the y back with an f inverse now, f inverse of x. And you've got your final answer. Let's check out 19 and 20, the last problems. Will the inverse of the following graphs be functions? So if I'm looking at these graphs, all 19a, b, 20a, and 20b, they are functions, and if it was a graph, I would be checking by using the vertical line test. Okay, everywhere it would work. Now, if I want to check if the inverse would also be a function, then I use the horizontal line test. Okay, so the horizontal line would be something that went from left to right this time, and I'm just dragging this up and down. Now I can tell that I'm failing this at multiple points. So just right there, I'm failing because I hit this point. Let me pick a different color. This point here and this point at the same time. So this one, I'm going to go ahead and put, oh, maybe not in highlighter. No. And just put it fails and I'll just for short put HLT, horizontal line test. For 20, even though I know this one's a little tougher to see, maybe I'll just put a new one down. I know this part right here looks a little suspect, but it's actually okay. Everywhere passes, so this one, the inverse would be also a function, and I would say passes the horizontal line test. All right, and I don't think that we had it show up here. No, it didn't, but that's it.